It is a code requirement to install a bonding bushing or grounding locknut on a 3/4-inch flexible conduit with number 6 aluminum conductors if it is not on the line side of the service, as stated in 250.94 of the National Electrical Code. The grounding locknut or bonding bushing provides a means for the flexible conduit to be grounded to the electrical system. This helps to ensure the safety of the installation and prevents the buildup of static electricity. The bonding bushing or grounding locknut should be installed at the point where the flexible conduit enters the disconnect for the heat pump. According to 250.94b of the NEC, a bonding bushing or grounding locknut is not required on a flexible conduit if any of the following conditions are met. Firstly, the flexible conduit is 6 feet or less in length. Secondly, the flexible conduit is connected to a grounded metal enclosure on both ends. Thirdly, the flexible conduit is used to connect to equipment where bonding is not required, for example, double insulated equipment. Since the flexible conduit is not on the line side of the service and is not connected to a grounded metal enclosure on both ends, it is required to have a bonding bushing or grounding locknut installed at the point where it enters the disconnect for the heat pump, as per the NEC 250.94. Grounding and bonding are critical concepts in electrical systems, aimed at ensuring safety and preventing electrical hazards. Grounding refers to connecting electrical circuits or equipment to the earth, providing a low impedance path for fault currents to flow back to the source. This path facilitates the operation of overcurrent protective devices such as circuit breakers or fuses, which interrupt the circuit and prevent electrical shocks or fires. Bonding, on the other hand, involves connecting metallic parts of an electrical system together to create an electrically conductive path. This path ensures that all metallic parts are at the same electrical potential, minimizing the risk of electric shock if a fault occurs. The NEC, or National Electrical Code, provides comprehensive guidelines for grounding and bonding to ensure safe electrical installations. Section 250 of the NEC is dedicated to grounding and bonding requirements, covering various aspects of electrical systems. These requirements aim to minimize the risk of electrical shock, fire, and equipment damage. Several key components are involved in grounding and bonding systems. Firstly, the grounding electrode system. This system consists of electrodes such as ground rods, ground plates, or metal underground water pipes that are connected to the earth. The grounding electrode provides a reference point for the electrical system and helps to stabilize voltage levels. Secondly, the equipment grounding conductor. The equipment grounding conductor is a conductor that connects the non-current carrying metal parts of electrical equipment to the grounding electrode system. This conductor provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices to operate. Thirdly, the bonding jumpers. Bonding jumpers are conductors that connect metallic parts of an electrical system together to ensure electrical continuity. These jumpers help to minimize voltage differences between metallic parts, reducing the risk of electric shock. Fourthly, the ground fault circuit interrupters, or GFCIs. GFCIs are devices that monitor the current flowing in a circuit and detect any imbalances that may indicate a ground fault. If a ground fault is detected, the GFCI quickly interrupts the circuit, preventing electric shock. In various scenarios, specific grounding and bonding requirements apply. For example, in residential electrical systems, the NEC requires a grounding electrode system to be installed, typically consisting of a ground rod or metal underground water pipe. The equipment grounding conductors must be properly connected to the grounding electrode system to provide a low impedance path for fault currents. In commercial and industrial electrical systems, more complex grounding and bonding requirements may apply. These requirements may include the use of multiple grounding electrodes, supplementary grounding conductors, and equipotential bonding to minimize voltage differences between metallic parts. Flexible metal conduit, or FMC, is often used in electrical installations to provide mechanical protection and flexibility for wiring. However, FMC is not considered an effective grounding conductor on its own, especially in circuits with high fault currents. Therefore, additional grounding and bonding measures are typically required when using FMC. One common method for grounding FMC is to use a grounding bushing or grounding locknut. These fittings are designed to provide a secure electrical connection between the FMC and the equipment grounding conductor. The grounding bushing or locknut has a set screw or other means of clamping onto the FMC, ensuring a reliable electrical bond. According to NEC 250.94, a bonding bushing or grounding locknut is required when using FMC to connect equipment if certain conditions are met. Firstly, if the FMC is longer than 6 feet. Secondly, if the FMC is not connected to a grounded metal enclosure on both ends. Thirdly, if the FMC is used to connect equipment where bonding is required. In these cases, a bonding bushing or grounding locknut must be installed at the point where the FMC enters the equipment enclosure. The bonding bushing or grounding locknut must be properly sized for the FMC and the equipment grounding conductor. It must also be installed in accordance with the manufacturer's instructions. When selecting a bonding bushing or grounding locknut, it is important to choose a fitting that is listed and labeled for the intended application. Listed and labeled fittings have been tested and certified by a recognized testing laboratory, ensuring that they meet applicable safety standards. Improper grounding and bonding can have serious consequences, including electric shock, fire, and equipment damage. The electric shock can occur if a person comes into contact with an energized metal part that is not properly grounded. The current flow through the person's body can cause muscle contractions, burns, and even death. Fires can occur if a ground fault causes excessive current to flow through conductors or equipment. The heat generated by the excessive current can ignite nearby materials, leading to a fire. Equipment damage can occur if a ground fault causes voltage surges or other electrical disturbances. These disturbances can damage sensitive electronic equipment and cause it to malfunction. To ensure safe electrical installations, it is important to follow the grounding and bonding requirements of the NEC. These requirements are designed to minimize the risk of electrical hazards and protect people and property from harm. Always consult with a qualified electrician to ensure that your electrical system is properly grounded and bonded. Regular inspections and maintenance of electrical systems are also important to identify and correct any grounding or bonding deficiencies. This includes checking the condition of grounding electrodes, equipment grounding conductors, and bonding jumpers. It also includes testing GFCIs to ensure that they are functioning properly. By following these guidelines, you can help to ensure the safety and reliability of your electrical system. The use of aluminum conductors introduces additional considerations for grounding and bonding. Aluminum is a good conductor of electricity, but it is also more susceptible to corrosion than copper. Corrosion can increase the resistance of electrical connections, which can reduce the effectiveness of grounding and bonding systems. To prevent corrosion, aluminum conductors should be installed with compatible connectors and fittings. These connectors and fittings are typically made of aluminum or a bimetallic material that is compatible with both aluminum and copper. The connections should also be coated with an antioxidant compound to prevent the formation of oxides on the aluminum surface. In addition to preventing corrosion, it is also important to ensure that aluminum conductors are properly sized for the intended application. Aluminum has a lower conductivity than copper, so it is necessary to use a larger gauge aluminum conductor to carry the same amount of current as a copper conductor. The NEC provides guidance on the proper sizing of aluminum conductors in various applications. When using aluminum conductors in grounding and bonding systems, it is important to follow the manufacturer's instructions and the requirements of the NEC. This will help to ensure that the system is properly grounded and bonded, providing a safe and reliable electrical installation. The role of overcurrent protection devices in grounding and bonding is critical to ensure safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of electricity in a circuit when the current exceeds a predetermined level. This protects the circuit and the equipment connected to it from damage caused by overloads or short circuits. In a properly grounded and bonded electrical system, overcurrent protection devices play a key role in clearing ground faults. When a ground fault occurs, a large amount of current flows through the equipment grounding conductor back to the source. This high current trips the circuit breaker or blows the fuse, interrupting the circuit and preventing electric shock or fire. To ensure that overcurrent protection devices can effectively clear ground faults, it is important to select devices with the appropriate interrupting rating. The interrupting rating is the maximum amount of current that the device can safely interrupt. The interrupting rating must be high enough to handle the available fault current at the point of installation. It is also important to coordinate the overcurrent protection devices in an electrical system. Coordination means selecting devices with different trip characteristics so that the device closest to the fault will trip first, minimizing the impact of the fault on the rest of the system. The NEC provides guidance on the selection and coordination of overcurrent protection devices. In addition to circuit breakers and fuses, ground fault circuit interrupters, or GFCIs, also play an important role in overcurrent protection. GFCIs are designed to detect even small ground faults and quickly interrupt the circuit, preventing electric shock. GFCIs are required in many locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. By using appropriate overcurrent protection devices and ensuring that they are properly coordinated, you can help to protect your electrical system from damage and prevent electrical hazards. The practical application of bonding bushings and grounding lock nuts in various scenarios. Consider a scenario where you are installing a new heat pump in a residential building. The heat pump is located outdoors and is connected to the electrical panel inside the building using a length of flexible metal conduit. To ensure that the heat pump is properly grounded, you need to install a bonding bushing or grounding lock nut at the point where the flexible metal conduit enters the heat pump enclosure. The first step is to select the appropriate size bonding bushing or grounding lock nut for the flexible metal conduit. The size of the fitting should match the size of the conduit. Next, you need to clean the threads on the conduit and the enclosure to ensure a good electrical connection. You can use a wire brush or a thread cleaning tool to remove any dirt or corrosion. After cleaning the threads, apply an antioxidant compound to the threads to prevent corrosion. The antioxidant compound will help to maintain a good electrical connection over time. Install the bonding bushing or grounding lock nut onto the conduit, making sure that it is securely tightened. If using a grounding lock nut, make sure that the lock nut is properly seated against the enclosure. Connect the equipment grounding conductor to the bonding bushing or grounding lock nut. The equipment grounding conductor should be sized according to the NEC. Once the equipment grounding conductor is connected, tighten the set screw on the bonding bushing or grounding lock nut to ensure a good electrical connection. Finally, inspect the installation to make sure that everything is properly connected and tightened. Use a multimeter to verify that there is a good electrical connection between the conduit, the enclosure, and the equipment grounding conductor. In another scenario, you are installing new lighting fixtures in a commercial building. The lighting fixtures are suspended from the ceiling using flexible metal conduit. To ensure that the lighting fixtures are properly grounded, you need to install a bonding bushing or grounding lock nut at the point where the flexible metal conduit enters the fixture enclosure. The installation process is similar to the previous scenario. You need to select the appropriate size bonding bushing or grounding lock nut, clean the threads, apply an antioxidant compound, install the fitting, connect the equipment grounding conductor, and tighten the set screw. In both of these scenarios, it is important to follow the manufacturer's instructions and the requirements of the NEC. This will help to ensure that the electrical system is properly grounded, providing a safe and reliable installation. Remember that grounding and bonding are critical components of electrical safety. By following the proper procedures and using the correct materials, you can help to protect people and property from electrical hazards. In summary, the NEC 250.94 provides specific guidelines for when bonding bushings or grounding lock nuts are required with flexible metal conduits. These requirements are designed to ensure a safe and effective grounding path. Understanding these rules and applying them correctly is essential for all electrical installations.